Okay, so let's look at immunity. And when we take a look at immunity, we look at it in two ways. One is called non-specific and the other one is specific. We'll discuss non-specific first, which is it doesn't matter what the invader is, this kind of immunity kicks in. And specific immunity is based on some specific pathogen entering the body or some specific thing like a graft or a transplant or something like that, and how the immunity kicks in, okay? So let's discuss this, which is non-specific. So obviously it's not specific to any pathogen, will kick in when anything comes in. And here we divide it into two lines of defense based on how the body is breached. The first line of defense is the physical barrier that your body provides. So on the outside of your body is skin, right, which forms a covering. So the first thing, if anything has to come from the outside and go in, it should either penetrate through skin and get in. So that would be skin. Or the second would be your mucous membrane. So for example, everything doesn't have to necessarily go through skin, but let's say something went through your mouth, right? Whatever lines the inside of your mouth, which is your epithelium. Same way with your nasal cavity. If you breathe something in and a pathogen, a virus goes in through there, so that again, the lining, which is known as the mucous membrane. Similarly, covering your eyes, the lining of your entire gastrointestinal tract, your entire urinary tract, all that is what is known as mucous membrane, okay? So this is the first line of defense, and this first line of defense acts, oops, sorry, don't answer that. The first line of defense acts like a barrier, a physical barrier, and how it does it is, for example, in skin. Skin produces sweat, which is a bit acidic, has antimicrobial properties. Also, when you sweat, the sweat kind of tends to flush off whatever pathogens settle down on the surface of the skin, so it flushes it off. Keratin is a thick protein made of dead cells. Again, that gets, you keep shedding it off, so that also helps. Plus, it is a thick barrier, so it helps to prevent certain pathogens from getting in. Acid in the stomach pH is obviously acidic, so prevent anything which is acidic usually tends to prevent antimicrobial colonization, so microbes are prevented from multiplying. In your saliva and your tears, you produce substances which are known as lysozymes. This is different from lysosomes. Remember, lysosomes were cell organelles which were suicidal sacs. These are lysozyme. Look at the spelling, okay? There's a zyme. These again have an antimicrobial property, and plus tears and saliva again tend to flush things out. So, when you cry, if something is settling down, it'll flush it out. Same thing with saliva. As also in the urinary tract, so urine usually tends to be a bit acidic. Plus, normally you pass urine all the time, and that tends to flush things out, which is why when you don't pass urine, when urine tends to stagnate, people end up having urinary tract infection, okay? Like if someone has a stricture or something that prevents urine passing out normally, so it kind of is constricting there, so it tends to stagnate, and that causes colonization, which is why they tell you to, pass urine frequently. Mucus produced by mucous membranes, for example, the lining of the respiratory tract has goblet cells that produce a lot of mucus, and they trap particles, and again, they help to get rid of them. Certain substances, some of this mucous membrane also produce substances known as defensins, which, as the name itself suggests, is a defense mechanism which is produced. They again help to get rid of pathogens, so antimicrobial property. So you can see how skin and mucous membrane, in a variety of ways, they either flush it out or prevent colonization of the microbes, which in other words means multiplication of the microbes. The second line of defense, let's say the first line of defense was breached, okay? It's like, in a war, your first sort of set of troops. If that is breached, you have to have a backup plan. The second line of defense is either by cells acting in a particular manner, and these will be all the cells that you learnt about, or it'll be certain chemicals which are produced. So let's look at some of them. in the second line of defense, we have cells which are capable of phagocytosis. So can you tell me some of the cells you know which are capable of phagocytosis? Macrophages, yes. Neutrophils, very good. Monocytes, which really turn into macrophages. And you may not remember them, but in many parts of the body we have this. In the epidermis of skin, and think back on ANP1, there was something called the Langerhans cells. That brings back memories, right? Also known as dendritic cells. Then in the nervous system, remember there was something called microglia, right? They were also phagocytic. So phagocytic cells, what they do is, you can see phagocytosis means cell eating. So it engulfs a pathogen, the pathogen goes inside, and that's where then the lysozymes take over and they kill this off, okay? Then in the body we have something which is known as natural killer cells. The arrow really should be pointing here. Natural killer cells are lymphocytes, and they are special type of lymphocytes, large, they're very, very large. What they do is they go and attach to a cell or a pathogen which has come in, and they will they kind of stick to it, and what they do is inside this natural killer cell you have these little vesicles present which liberate something known as perforins. As the name suggests, what these perforins do is they go and perforate the cell membrane. So the entire cell just kind of blows up or gets lysed. Okay? So that's what natural killer cells do. They are usually effective in cancer, in taking care of cancer cells or virus infected cells, and we'll do more about them. The third type of second line of defense is what is known as inflammation. So I'm going to leave this for now, and we'll look at inflammation in a little bit more detail. So inflammation consists of, again, cells coming to that part, and the idea of inflammation is to make sure that whatever injurious stimulus has come in, it kind of localizes it to one spot so it doesn't kind of spread around. And you might have all had some sort of inflammation at some point in your life, let's say a thorn pricks you, that area gets red and swollen, or something bites you, that area gets red and swollen. So it's just localized there, it prevents it from spreading elsewhere, and then it causes repair in that area. So the purpose of inflammation is to localize and cause repair of the damaged tissue. And we'll see a little bit more of it in detail in a few slides. Let's move to the next second line of defense, which are antimicrobial microbial proteins. These are proteins which are produced. There are two of them. One is known as interferon. So when a virus gets inside a cell, that cell produces interferon. It itself is damaged, but it kind of thinks, I'm damaged, but let me help out the other cells. So what it does is it produces this protein called interferon, which goes out and goes to the other cells. And it prevents the viruses spread by multiplication or replication. One virus will get inside your body and it will multiply and it become millions of clones of the same virus. That's how viral infection spreads. So if you can stop that, obviously you can stop the spread of that infection. So if a cell is damaged by a virus gets inside the cell, that cell is dead. I mean, it's done for. Nothing, you can't help that cell. But that cell produces interferon, which goes out and helps all the other cells, where it prevents the virus from replicating in those cells. So then, in other words, it cuts down the lifespan of that virus. So that's how it helps. Okay, so that's one way that this interferon helps. The second thing that interferon does is it activates these natural killer cells. And remember, I said natural killer cells help to take care of virus infected cells. So when it activates natural killer cells, they go and attach to cells which are infected by the virus, produce perforins, and that causes lysis of the cell. It also causes macrophages to be activated. Macrophages will come if a virus is lying loose, it'll engulf it and take care of it. Okay, so interferon kind of helps in three ways. And interferon is not virus specific. So if let's say the chickenpox virus comes in, when interferon is produced, it can help some other virus like measles. Nowadays a lot of talk is going on about measles. In fact, interferon is being used a lot of research is being done on interferon nowadays to give people who are suffering from some viral infections, they give them interferon. The other type of antimicrobial protein is something known as complement protein. It is like when we did clotting of blood, if you remember clotting, we said there were many factors and one factor kind of caused the activation of another and then it caused the activation and finally you ended up with fibrin threads being formed. Same way, complement consists of a series of proteins. You don't have to know the names of those proteins, but it is present in your body in an inactive form. It gets activated, and once it gets activated, it sort of one protein will activate. It's like a cascading effect. One protein will activate, another one will activate another one. And what it finally does is that if this is the cell, these proteins get activated one on top of the other like this. So it kind of makes a hole in the cell, and the entire cellular contents kind of just, the cell gets lysed. It completely bursts, okay? So that's how complement protein acts. Complement also promotes phagocytosis, so it brings about cells which are capable of phagocytosis, so takes care of any debris which might be lying there. And one important thing about complement is that it acts both in specific and non-specific immunity. So here we are discussing non-specific immunity. When we discuss specific immunity, you will see that antigen-antibody complexes, they activate complement. So it acts in both specific and non-specific immunity. Then we have fever. You all know you've all had fever in your body at some point or the other. It's really a good thing. It's the body's way of speeding up repair. That's the purpose of fever. What it does is it makes substances like iron and zinc unavailable. The liver and spleen sequester iron and zinc. And when this iron and zinc is made unavailable, the pathogens actually need that in order to do their job. So when it's unavailable, they no longer have that. Of course, extreme fever is really bad because when your fever gets really high, your body thermostat goes awry. And what it does is it denatures proteins. That is why whenever someone has fever which is really, really high, let's say 105, we always want to bring it down quickly because high fever can denature proteins in your body and enzymes. And those enzymes are important for regular, day-to-day activity of the cell. So that's why we're worried about them. But having fever of 99 or 100 is really not all that bad because it really speeds up repair. Yeah? What about? Heat flashes? Like hot flashes, which you're talking about, which menopausal women get. That's not fever. That's because of lack of hormones that your thermostat kind of acts differently. So that's not fever that you're getting at that time. That hot flashes don't serve any purpose. It's just because your hormone levels have just dipped down so much. Okay? So here let's take a look at how complement acts. Okay, it looks like that's not working. Let me try one more time. Okay, we'll move on. Okay, let's take a look at this question. Which of the following are produced by the skin to provide the first line of defense? Okay. How many of you have had mucus on the surface of your skin? I don't think, right? You wouldn't want do you want all that slippery stuff on the surface of your skin? Mucus is produced by columnar cells, cells with a lot of cytoplasm, and goblet cells, right? Remember, your epidermis, which is stratified squamous keratin, the top layer keratin is dead. You can't produce mucus. So it only produces keratin and sweat. So the answers would be just B and C, which only 19% of the class got right. Okay? No mucus.
Too many alternatives. That's why.
What's that?
Too many alternatives.
Oh, too many alternatives? Okay. Okay, let's take a look at inflammation, which I told you we'll stick to it. Talk about it later. So inflammation is that something has injured has breached the first line of defense, has come in here, and it damages tissues. And so inflammatory chemicals are liberated, and they act as what are known as chemotactic agents. And they kind of, because of these chemicals, cells are kind of drawn towards it. So these phagocytic cells arrive at that area where the damage is done so that they can take care of the cell debris. And they arrive there because the blood vessels in that area, because of these inflammatory chemicals, and you've seen basophils, for example, producing histamine and heparin, right? They cause vasodilation. Basophils are very few in number, but we also have mast cells which are present. You may have read about it in ANP1. They are tissue cells, again produce histamine and heparin. So when they produce these substances, the blood vessels dilate. When they dilate, the capillary permeability increases because between the endothelial cells, the pores get really large. And so these cells, these phagocytic cells, they can actually pass through. When they get out of the capillaries, that process by which they get out through an amoeboid movement is known as diapedesis. They come to that area. Because more, oh, my thing is so sensitive. Because capillary permeability increases, a lot of tissue fluids, oh my God, this is tissue permeability increases in this area, and when tissue permeability increases, it causes swelling. You may also have seen that that area looks red and raised. That raised thing is because of swelling. The redness is because capillary permeability has increased. More blood is flowing through that area, which is why it becomes red. So redness is known as rubor. Swelling is tumor, to cause swelling in that area. That swelling puts pressure on the nerves which are in that area, and that causes pain. And because of the swelling, you also have heat. You know, have you ever touched an inflamed area that feels a little hot? Because vasodilation means more blood flowing through that area, so it causes heat, which is known as calor. These are some of the things that we see are parts of inflammation. You have heat, which is known as calor. You have redness, which is known as rubor. You have swelling because of vasodilation. That area has more fluid there. That is like a tumor, so it's called tumor. And dolor is pain because the nerve endings are compressed. And you also will have loss of function of that area if the swelling is really large, okay? So the purpose is that you remove, all of this is localize that region so that it doesn't spread, and you kind of speed up repair. So here let's take a look at inflammation. Hopefully this will work. Oh, I don't know why that's happening. Okay, I don't think we can connect to the internet today. Yeah. Let me see why. Okay, well, next we'll look at these next time. I'll check this out. So, okay, let's take a look at this question. What does chemotaxis mean? Very good. Yes, it is attraction due to chemicals, and you saw in that picture. So that's why it's really important to look at the slide very, very carefully. Most of your answers are often given in the slide. Here, let's see which of these is not a feature of inflammation. Okay, I'm glad you all chose mucus this time. Yes, mucus and lysozymes are not released at this time. Yes. Okay, another. Which of these best describes the purpose of inflammation? Very good. Yes, the purpose. All of these happen. It does increase the blood supply, it does localize, and does remove the cell debris. But the last statement kind of encompasses everything else. So it does localize and promote repair. So the next two slides are really good about the first and second line of defense. Basically, this is a review. So make sure you kind of look at this so you can see the first line of defense, surface membrane. So skin and mucous membrane. So look at the acid in the skin, makes it acidic, prevents bacterial growth. Keratin by itself is resistant, prevents substances getting in, and provides resistance against bacterial enzymes because it's quite thick. Mucous membrane, if there's mucus, it traps microorganisms, hair like cilia, and just hair itself traps them. Gastric juice is hydrochloric, protein digesting, destroys pathogens, prevents them from colonizing. Lacrimal secretion, urine, so you can see they flush it out, they cleanse that area, they contain lysozymes, which destroys microorganisms. And second line of defense, again, you can see the phagocytes, natural killer cells, inflammatory process, interferon, complement, and fever. So this is a good review slide. Your PowerPoint really is, you must look at the PowerPoint with your notes because I've tried to put all the slides which kind of give you a visual representation of that. So a lot of your answers are up here. So let's see if you got a question like this. A foreign body enters your eye and irritates your conjunctiva. So this is why you can never forget ANP1. You're in ANP2, but you really need to remember some of those things. Causing you to tear up. Which line of defense has been breached? Excellent. Yes, first line of defense, because your conjunctiva is a mucous membrane, right? And so that's the first line of defense, producing tears which kind of flush that out. Again, a lot of questions on this one, so I want to make sure you all get this clear, which is incorrect. Good. Cells and chemicals were the second line of defense. So phagocytic cells are not the first line of defense. This HCl and lysozymes do inhibit microbial activity, and mucus in the respiratory tract, because that's the lining, which is a mucous membrane, it does act like a first line of defense. Now let's look at specific immunity, where now we are talking about specific pathogens. This is often called a third line of defense. This is two types. One is called humoral, that means there's something in the blood plasma, and the other one is cell mediated, which is a cell to cell reaction. So cell mediated is a cell to cell reaction. And this is something known as antibodies. And you've already done this when we did blood. You did one type of antibodies. Remember when we were talking about blood groups? Someone has antigen A, then in their plasma they have antibody B, right? So these are antibodies which will be produced by certain cells in blood, and where in blood it will be present in the plasma. Since first the particular cells have to recognize this pathogen, which is an antigen which comes in, and then mount the immune response, it takes a little longer to bring about. Unlike non-specific, it just happens anytime. It's like, you know, you go shopping and someone tells you, buy anything you want. Easy, you can just go buy some. When you go look for something specific, it takes a bit longer to do that. Same thing up here. It's antigen specific, and you'll see how a cell is kind of programmed to react against a specific antigen. So if a particular lymphocyte was programmed to react against measles virus, that lymphocyte will not react against chickenpox or yellow fever or anything else that comes in. It just reacts against that. So it's antigen specific. Priming is needed. It's like when the party starts, they've got to be introduced to each other. Okay, so that's why you'll see that they have receptors. These lymphocytes will have receptors on the surface of their cells. If the receptor is for that particular antigen, it will react with it. If the receptor is not, it will not. So it's kind of got to be introduced to the antigen. Then it's like how when you go to a party and you're introduced to someone, usually you kind of tend to remember their names. I know some people are not good with names and some people are not good with faces, but we are lucky that our immune system is good with both names and faces. So the immune system kind of, the first time it's introduced, it goes into its memory bank, and it actually produces what we call memory cells. And so they remain in your body, and you'll see how the next time it's introduced, and this is really like very similar when the first time you're introduced to someone, and let's say you meet them after some time, you may not remember their name or their face, but you know, they look familiar to you. So your response to them comes out a little faster. Same thing happens because of the presence of your memory cells. If that same antigen comes into your body the second time, or any other subsequent time, the response will be much faster. So we'll see how, this is why we get vaccinated. And so that when you get shots, it is so that your body kind of starts producing memory cells, so that when the antigen comes into your body the second time or any other subsequent time, it responds quickly and takes care of it, and you never suffer from that infection, okay? And specific immunity is systemic. It's not localized. It affects the entire body, spreads out, so it's systemic. So these are some features of specific immunity. So let's look at some of the terms that we see in specific immunity. The first one is what are antigens. We talked of antigens when we were doing blood grouping. So we said, you know, Rh antigen or antigen A or antigen B. Remember, those were present on the surface of red blood cells. Here we have antigens which are not just limited to blood cells, they are all over. These are protein in nature, or they may be even carbohydrate, sometimes it may be lipids or nucleic acids. These are seen on the external surface of cells, just like those blood group antigens were on the external surface of RBCs. Here antigens are seen on the external surface of cells. They are substances which are provocative. They provoke an immune response. You call it an antigen when it provokes an immune response. And these are seen they're kind of like flags which are displayed by something known in your body as Mhc proteins. Mhc stands for major histocompatibility complex. So inside your body, you have these glycoprotein markers which are present. They belong to you. So we call them self-MHC proteins. What they do is they are present as markers on the surface of the cell. Your antigens, which every one of us has antigens on the surface of our cells, this MHC protein kind of breaks down those antigens, and it puts it on the surface of the cell, raising it like a flag. Lymphocytes, which are the ones, main cells which take care of specific immunity, they pass this and they say, oh, this is self, we are not going to destroy it. They take care of that. I mean, they pass out. They don't harm that cell. But let's say some other kind of antigen gets into your body. It gets inside a cell. This Mhc proteins, which are present inside, they process it and they raise another flag. So here's your self antigen being displayed, which your lymphocyte will normally ignore. But here is a non-self antigen which is being displayed, which now your lymphocyte says, oh, that looks foreign to me. I need to take care of it. And that's when the immune system will be provoked. Okay? So that's a function of the Mhc proteins, to kind of process the antigen and display it on the surface of your cells. In your body, sometimes there are, or this happens all the time, there are antigens which are present in your body which are kind of kept away from blood. These antigens are, it's like they are in solitary confinement. So we call them sequestered antigens. Good examples of sequestered antigens are the lens of your eye and sperms. Sperms. Lens of your eye and sperms. These, in other words, the body never came in contact with them. The blood of your body never comes in contact with them. So if at any point it does come in contact, it thinks of it as foreign. It's like, imagine you had relatives who you never knew, and then one day that relative is introduced to you without anybody telling you. You think that person doesn't belong to your family. Same thing happens with these sequestered antigens. So since lens was never introduced to the body cells anytime during development, the antigens of the lens, the body thinks of it as foreign. Sperms too never come in contact with the blood of a male. So if the sperm somewhere were to leak out, the body would recognize it as foreign and invaded. This is the reason why when they remove the lens in a cataract operation, they're always very careful never to pierce the lens. If they kind of break the lens, and pierce the outer shell of the lens and the fluid would come out, you could set up a violent reaction, because, the fluid will pour out the antigens and the body will think of it as foreign. When males undergo what is known as sterilization, which is vasectomy, the two ends of the vas deferens are tied off, or there are different ways to do it, but let's say the two ends are tied off like this. So here is one closed end and here's the other closed end. Sperms are still produced by the testes, just now that the sperms cannot travel further in the vas deferens. If for some reason this area was not tied off properly, sperms would leak out and they would lie in the testicular area and in the scrotum, and they could set up a violent reaction. So that's why it's very important to tie these off, because these two are known as sequestered antigens. Okay?
So if you, it's kind of weird, but if you, say a guy has a huge cut or an open wound or something and gets sperm in that, is that going to make this huge infection?
Probably. Could be. I mean, yes. Okay. Probably would. Yes, it would. If they were to get. Yes, it could happen. Yes, it could happen, because it is, if it can happen I've never been asked that question, but yes, if it happens in the, in the scrotum, it could happen outside anywhere else too. Yes. What's that? The sequestered antigen? Right. Well, in her case, it wouldn't affect her so much, because sperms are foreign anyway in her body, and they don't affect her. But and in the woman, it's very strange, which is why like the woman doesn't, the fetus, the embryo has half of the male things, but the woman never kind of dislodges the embryo, like it lets it embed and develop. So there's a different sort of process going on in women. But in the male, it belongs to self, but the body doesn't recognize it as self. So in a woman, it won't affect her. You see, got that? Yeah, that's why it's sequestered in him. Okay. got that. But yeah, good question. Yeah.
Do females have any sequestered?
Lens? No. Maybe they do, but none that I know more
Yeah.
that I know of. Okay.
Thanks.
Okay, so here let's look at immune system cells. And there are three basic types of immune system cells. APC stands for, and we will be talking about this all the time, this is called antigen presenting cell. So that means these are cells, if an antigen enters your body, these are cells which will engulf the antigen, then the Mhc protein inside will process it, and then it will raise it as a flag in order for it to be recognized by the lymphocytes. So that's why they're called antigen presenting cells, and we'll see how this happens. So these are the different types of antigen presenting cells are dendritic cells, like your Langerhans cells were called dendritic cells. There are many such dendritic cells all over the body, macrophages and certain B lymphocytes. The other type of immune cells are B lymphocytes, which take part in that humoral immunity, and T lymphocytes, which take part in what was called cell-mediated immunity. And T lymphocytes are of three types. We'll see them later when we discuss them. One which are known as cytotoxics. Cytotoxic, as the name suggests, they are toxic to cells. These are the main cells which actually take part in cell-mediated immunity. They are the ones which will latch on to cells and kill them. Then we have ones called helper T cells. These are extremely important in the immune system. You may want to write this down right here. Extremely important because these helper T cells, as the name suggests, helper, these help both in cell-mediated and in humoral immunity. In fact, if helper T cells are not there, your immune system pretty much will shut down because you do not have these to help cell-mediated and humoral immunity. And then we have cells called suppressor T lymphocytes, which when the immune response has reached the level what you want it to be, they turn off the immune system. Because if they didn't, you would keep doing what was being done, and then there would be an imbalance. Okay, so they suppress the immune system when you don't need further immune response to occur. Okay.
So things like cancers and AIDS, when their immune system is decreased, do they have a lack of helper cells?
Yes, actually we will discuss that in AIDS. That's what happens in AIDS. The helper T cells are the ones which are getting killed off. Okay. So in the immune system, remember, yeah. Say that again.
You said the B lymphocytes for the APC, there's only a certain amount. Do you have to know that for the test, or do you just think that that's APC?
Yeah, that certain B lymphocytes can also be antigen presenting.
Okay.
You can't sort of label them separately. Okay, there are certain B lymphocytes which are antigen presenting, and B lymphocytes also happen to take part in the humoral immunity.
Okay, so we just have to know that.
Yeah, just that, yeah. So you remember when we did lymphatic system last time, we talked of primary lymphoid organs, which were red bone marrow and the thymus. You remember that? And then we had the secondary lymphatic organs where we talked of lymph nodes and tonsils and spleen and the follicles which were present in walls of other organs. So here's a reason why we have these primary lymphatic organs. And this is very similar to, imagine a recruit who signs up to go into the army. Okay? So this guy needs to be trained. He wants to go into the army, but he's going to be no good unless he gets trained. So let's say he has the opportunity to go to West Point. He goes to West Point and gets trained. He's trained, but he is still naive because he hasn't taken part in a war. So unless he kind of actually goes to war and does his job, until then he really would be naive, isn't it? Our immune system is pretty much the same way. The two organs like the bone marrow and the thymus are like West Point. where lymphocytes are kind of sent to get trained. In here, the training is what is known as immunocompetency. There we would call it military competency if they were going, right? They are still naive. So what happens is that they go off to the various secondary lymphatic organs and they settle down there. And then after that, it's only when they get introduced to the antigen that they can bring on their skills that they were taught during their training, that they're capable of mounting the immune response. Okay? So let's see how that happens. So during fetal life, in the bone marrow, mainly in the diaphysis, but in the bone marrow, also in the epiphysis and other areas, you have these lymphocyte precursors which are being formed. Still in fetal life, these lymphocyte precursors get sent to the thymus, and some of them remain in the bone marrow itself. Those that get sent to the thymus achieve immunocompetence, and these will be known as T lymphocytes. So T lymphocytes achieve immunocompetence or training in the thymus. Remember these? So that's why they're called thymus-dependent lymphocytes or T lymphocytes. Those that remain in the bone marrow, they achieve immunocompetency and they become B lymphocytes. So these guys get trained to take care of cell-mediated immunity, and these guys get trained to take care of humoral immunity. Okay? So it's like these guys get trained in the army, they get trained to take care of tanks, and these guys maybe are in the infantry or something like that. Okay? It's called T lymphocytes, thymus-dependent lymphocytes. It's called B lymphocytes, and it would be easy to think it's called B lymphocytes because of the bone marrow, right? But it's really not because of that. In the chicken, there was something known as bursa, and it's the B of this, bursa of Fabricius, where they first noticed that this development was occurring, and that's why it got its name from the B. But it's helpful for you to remember the B, bone marrow, so B lymphocytes, okay? But it actually comes from there. So here they are trained. It's like they went to West Point, they got trained, but they are still naive. They haven't yet sort of been introduced to anybody, okay? When they get trained is, what happens is there'll be lymphocytes, for example, which will be trained against measles. There'll be lymphocytes that will be trained against chickenpox. There'll be lymphocytes against streptococcus. So for every antigen, there are a group of lymphocytes which are trained, okay? Remember, it was antigen specific. There's a specific immunity. From there, these cells go to the various organs like lymph nodes, spleen, lymph follicles, all over there. And as we said, that it's still naive. Then when a lymphocyte comes in, it has all these lymphocytes will have receptors on their surface. Remember, those receptors are antigen specific. When the lymphocyte reacts or encounters an antigen, it gets activated. Now it's the first time it's being introduced, so now it gets activated, and only then is it capable of doing its job. Only then does it carry out its immune response. And the immune response is you'll see that it actually produces a colony of similar lymphocytes. So because if you get introduced to one, you need a big army to take care of it, right? So that lymphocyte, when it gets activated, it'll clone and produce many lymphocytes very similar to it. So your body kind of has so many of these lymphocytes which will be able to take care of that infection. Okay? So have you understood this thing? That initially in the bone marrow, the lymphoid precursors are formed. They're sent to the thymus and the bone marrow to become immunocompetent. In the thymus, the T lymphocytes get immunocompetent, and in the bone marrow, the B lymphocytes get immunocompetent. Once they are trained and become immunocompetent, these T and B lymphocytes go to all the other lymphoid organs and they settle down there.
And they both reproduce, both B and T?
Both B and T will reproduce, right? When they meet an antigen, then they get activated because they have to be specific for that antigen. When they meet their specific antigen, they get activated. They produce what is known as a clone, and you'll see that they also will produce memory cells so that it can be kept in the memory bank, and that's when the immune response takes place. Okay? So here you can see how they will proliferate. You'll form many of them. So this selection process which occurs in the body, it really, when they were getting trained up there in the thymus or in the bone marrow, and here an example is being given of the thymus. This kind of is a very interesting way that they react, or they sort of are trained. The first is that, remember those Mhc proteins which are your markers, right? So here is a T lymphocyte which has come to the thymus to get trained. First, it must be able to recognize its own Mhc proteins, right? So look at this picture carefully, and I'm really scared to even move my mouse a little bit because it just keeps moving. So if you look at this picture here, notice here the T cells, they get trained. Here's a cell which has an antigen presenting cell which has its Mhc protein, which belongs to the same, it's called a self, to the person itself. So it's called a self Mhc protein. If there's a T lymphocyte which is not up to the mark, okay, it's not done its work, it fails to recognize the self Mhc protein, it will be killed off. So that is known as apoptosis, which is cell suicide. If a cell, on the other hand, a cell which has come for training, recognizes this Mhc protein as belonging to self, that it is a self marker, it will live and it'll go on to the next step. Okay, so this one is known as positive selection. So have you understood this? So they first have to recognize their own markers. They have to be capable of recognizing their markers. Like you have to recognize first your teacher before she gives you the test, right? You can't go to the wrong classroom. So same way, they have to recognize the marker that it belongs to self. If they are capable of recognizing it, they'll go to the next step. If they can't even recognize their marker, they die. Okay, so we are still at the markers. Next is these T lymphocytes which are undergoing training, you do not want them to recognize self antigens and react against them, because every time they recognize an antigen, they will react against them, right? So here, now we are talking about antigens. At this point, we were talking about Mhc proteins, which were markers. So they must recognize the markers. Now, we do not want them to recognize self-antigens, because when they recognize an antigen, they will react to it. So if they recognize self-antigens, they will react to it and produce an immune response. So if there is a cell which recognizes an antigen, it will react against it. We don't want that cell to be kept around, so that cell dies. So we eliminate it. So during the process of training, lots of cells die, because they are recognizing self. In other words, they are going to react against self. So it's like in an army, if you have recruits who can turn against you, you want to kind of weed them out of the army. You don't want them to be in the army. Okay, have you followed? So this is negative selection. That means those that recognize self, we want to get rid of them because they will react against them. Those that don't recognize self, so in other words, they are kind of, okay, they're not recognizing, which means they are tolerant towards it. Okay, I'm not going to react against you. Those are kept in the body and those will survive. Have you followed this? Okay. There are some cells which are iffy. That means they're not sure whether they recognize or they don't recognize. So what happens is they're kind of programmed to become immunotolerant. So they're kind of pushed here. So they are pushed towards not recognizing them. So these iffy kind of cells are pushed towards becoming immunotolerant and not recognizing, so that they won't recognize your body's antigens. You've all heard of autoimmunity, right? Many diseases like multiple sclerosis, there's a disease called Graves' disease, psoriasis, I mean, there's so many, type 1 diabetes, rheumatoid arthritis, all these. Here in autoimmunity, the body is actually attacking itself. That means it is recognizing these self-antigens, and when we say recognizing self-antigens, it's thinking of them as foreign, so it's beginning to interact with them. It's not being tolerant towards them. How autoimmunity happens is either some of these guys did not die, so they weren't removed, or probably due to some genetic mutation in the DNA or, environmental pollutants or something like that. Something changed. So now the cells, your own body cells, think of your self-antigens as foreign and they begin to react against it. So that's how autoimmunity happens, okay? So let's look at this question now. Very good. Yes, lymphocytes which react strongly against self-antigens, that means they recognize and they will react against them, they are killed. They are not kept against surveillance throughout life. Do you want to have I don't know if I should even use that example, but you do not want someone who's going to harm you. You don't want that thing lurking around your body throughout life and monitoring them. You'd much rather kill them off right away, right? So, lymphocytes... I realized I was probably going to be politically incorrect here. So the lymphocytes which react strongly against self-antigens are just killed off. They're not kept against surveillance. It's only those iffy ones which kind of become tolerant and then, they won't react against self-antigens. Here, next question. Mhc proteins. Which one of these statements, the answers completes the statement? Very good. Yes, they process and display self and non-self antigens on the cell surface. Okay, another one. Good, very good. Okay, so here let's look at humoral response. So one, it occurs in blood. B lymphocytes are the ones which take care of humoral response. So let's see some of the features. Occurs in blood. B lymphocytes take care of it. When we say it occurs in blood, this is because in this response, antibodies are formed. And if you remember, antibodies were formed in the plasma. Antigens are present on the surface of cell. Antibodies are present in the plasma. So that's why we say this is something that happens in blood. So in this B lymphocyte, again, remember, every lymphocyte is primed for one particular antigen. So on its cell surface, it will have a receptor which will react with that antigen if that antigen comes into the body. So in your body, you have these lymphocytes which are programmed for every kind of possible antigen. You may die hundreds of years later without ever having come with that antigen. So that lymphocyte remained naive throughout its life, right? It's like a soldier who was trained but never went to war. It's exactly like that, because if you never go to Africa, you may never come in contact with the yellow fever virus. So your immune system, that lymphocyte would never come in contact with that, okay? But we have these which have receptors which are programmed to react against specific antigens. So here's what happens the first time the antigen is introduced into your body. So that response is known as the primary response. As the name suggests, the initial encounter. So here are a bunch of lymphocytes with various receptors on the surface of their body, and an antigen enters, and that antigen, as we saw, could be a protein, a carbohydrate, lipid, nucleic acid. It could be a whole cell coming into your body, part of a cell, a virus, bacteria, anything. Only the one lymphocyte or only those lymphocytes which have receptors for that antigen will bind to it, okay, and they get activated. When they get activated, they begin to multiply, because they want a whole, it's not like when we say an antigen enters your body, it's not just one bacteria which enters your body or one virus which comes into your body, right? It's a bunch of them which get into your body. So similarly, you need to have many cells which can deal with that. So this lymphocyte gets activated, it multiplies and forms what is known as a clone, and those cells are exactly like it. That means they will have the same receptors, they will be able to produce antibodies against it. When the clone is formed, most of the cells in the clone get converted to plasma cells. So plasma cells, the B lymphocytes get converted. Most of them get converted into plasma cells. A few of them get converted into memory cells. The memory cells are those cells which kind of will now remember that antigen. These plasma cells are also known as effector cells. Remember when we did ANP1, we had something called the reflex arc. We had a stimulus, went through a receptor, and then it finally went through an effector, which was a muscle or an organ. Effector is the thing that produces the response. These plasma cells begin to secrete antibodies. So it's the plasma cells which secrete the antibodies. Those antibodies are secreted in the plasma. That's why they're called plasma cells. They secrete a whole heap of antibodies. Those antibodies, we will see, they will bind to the antigen. So that antigen is present in the extracellular fluid, either in blood itself or present in tissue fluid. It will react with that and form what is known as an antigen-antibody complex. Antigen-antibody complex. Now, it isn't as if you only get introduced to an antigen once in your lifetime. It may be, if you're living in an area where some kind of infections are very common, you can get repeatedly exposed. So the secondary response, the second time that same antigen comes into your body, it could be the very next month, or it could be years later. So any time it comes, or it could happen many times later. So the second and subsequent time that antigen enters your body, that response is known as the secondary response. Now you have those memory cells which were formed here, you have them floating around with the same receptors. But these guys they don't have that ice breaking thing going on. They were introduced to the antigen long back. Now they recognize the antigen immediately. So what they do is they do the same thing. They clone, form many plasma cells, and they form some more memory cells so that memory keeps living. But this response is done really fast. And therefore, the secondary response occurs really fast. So that's the purpose of forming these memory cells. This response occurs slowly, because first the cell has to recognize the antigen, then it takes time to form the clone, and then it proliferates and does all that. Here, because it recognizes it really fast, the response occurs very fast, and then the response is the same. Antibodies are formed and memory cells keep getting produced. This is why many of you may never have suffered from, you may never have had chicken, apart from the fact that you're vaccinated. But let's say that you are not vaccinated against every disease. Many of you may have never had a strep throat in your life, okay, or may not have had some other problems in your life, and that's because that antigen probably entered your body, but your immune system recognized it the first time, took care of it. Next time it came into your body, again, the reaction was real faster. It took, your immune system was good enough to take care of it. So you never ever felt the problem occurring. When you suffer from an infection, it's not because the immune system didn't work. The immune system did work. It did do all this, did produce the antibodies, did form clones. It's just that it got overwhelmed. So the amount that the immune system worked was not enough. And that's why you suffer from that infection. Okay?
They say, you know, when like little kids first go to school or daycare or something, they go through this process where they're sick forever.
Yes.
Like nurses in a new job or something
Right.
like that. Is this the primary response, and then once they re-meet these antigens, and then they become sicker, or is that the sort of secondary response? Or
When children go to the daycare, certain things like most of the time it's colds, you know, cold and ear infections that they often get. Things that they've been vaccinated against, they usually will not get that infection. Now here is the first time they get that infection. It's a viral infection, cold virus, the rhinovirus, you know, it can change. Sometimes you may, or flu, you may have different strains of the same virus. It's there, the children get the infection. The first time they get the infection would probably, we don't know whether it's a primary, because a primary may have occurred and you may not have even known about it. Got it? The reason they keep getting infected so fast is, one is they are young. The strains in viral, especially things like cold and flu, there are many strains. So the first time they got infected, maybe they formed memory cells against strain 1. But the second time they got infected, it could be strain 2, which is why when you get a flu shot, they predict that these are the possible strains it can protect you against. And you may still get the flu, but only the flu is not so much. So when they keep getting reinfected, yes, it is the secondary and so on, but then the immune system is getting overwhelmed, which is why they come up with the infection. There may be many times when they may have got the pathogen enter their body and the immune system took care of it, so they never came home with a sickness. Okay, so the primary response could have occurred way earlier. You don't even know when it occurred. Got that? And it's not that the first time they show the infection, that's when the response is. It could be where they may not even show that because the immune system took care of it. And children just get more prone to it in daycare. Everybody is so close. Children touch all kinds of things. And most of the time it is respiratory because it's going through it's an oronasal kind of pathway. Okay. So let's look at the antibodies that we talk of. We said these antibodies are produced. There are certain classes of antibodies. And let's look at the various classes of antibodies. We have antibody M, which is the first antibody to be produced. IgM are the first antibodies to be produced. Don't live for very long. Thereafter, we have antibodies called IgG. These are most plentiful. First time, yeah, but then they are short-lived. IgG are more plentiful. These are because usually you have a secondary kind of response, more plentiful. Then the third class of antibodies are IgA. These are types that are secreted in milk and saliva and tears. IgE antibodies are what are seen in allergic responses, allergies. IgE is the type of antibody that is secreted. And then we have IgD. They used to think the function was not known, but now they say their function is somewhat similar to lymphocytes. Okay, so these are the 5 classes of antibodies: IgM, IgG, IgA, IgE, and IgD. Ig stands for antibodies are also known, I took it for granted you would know, antibodies are also known as immunoglobulins. That's why we use the word Ig. They're also called immunoglobulins, and later when we talk of different types of immunity, we'll see we call it immune serum, because remember, antibodies are in plasma. So last time what happened was we couldn't see 2 videos, so I do want you all to take a look at those. So I'm going to go over those videos, The first one was inflammation, and after that I want to show you all complement system, which is important. So let's take a look at inflammation. We already looked at inflammation, so now this is kind of just going to review. So it's from the last class.
Yeah. Another one. Oh, dirty. Yeah. Come on.
Inflammation is the protective reaction of vascularized tissue to local injury. Acute inflammation is the early, almost immediate reaction of tissue to the injury, and it is the first phase of wound healing. Acute inflammation can be triggered by cell or tissue damage or by the presence of dead cells or noxious agents such as bacteria. Acute inflammation typically occurs before the immune response becomes established and aims primarily at removing the injury-causing agent and limiting the extent of tissue damage. Acute inflammation occurs in two overlapping stages, vascular and cellular. In the vascular stage, arterioles and venules near the site of injury constrict briefly, then dilate. Dilation promotes congestion, while an accompanying increase in capillary permeability leads to the movement of fluid into the affected tissue, resulting in the 5 classic signs of inflammation: redness, swelling, heat, pain, and loss of function. As fluid leaves the capillaries, the blood remaining in circulation becomes more viscous, it flows more slowly, and clotting occurs. The cellular stage of acute inflammation is initiated by the movement of phagocytic white blood cells, or leukocytes, into the area of injury. The leukocytes begin to adhere to the vessel wall, and then, in a process called emigration, squeeze through the wall and move into the inflamed tissue. The leukocytes wander through the tissue, guided by chemical signals in a process called chemotaxis. The cellular stage culminates in the leukocytes engulfing and degrading the bacteria and cellular debris in a process called phagocytosis. Products of phagocytosis, along with plasma and blood cells, form exudates, which accumulate, causing swelling and pain. Exudates are composed of serous fluid, red blood cells, fibrinogen, or tissue debris, and white blood cell breakdown products. Concurrent with the events of the vascular and cellular stages, chemical mediators release bioactive agents that act to mediate the inflammatory response. Mediators are derived from the cells or from plasma. One of the first mediators of an inflammatory response is a cell-derived mediator, histamine, found in high concentrations in the mast cells of connective tissues adjacent to blood vessels, as well as in blood basophils and platelets. Histamine is released in response to a variety of stimuli and causes dilation and increased permeability of capillaries. Serotonin, another cell-derived mediator, performs similar actions. The 3 major plasma-derived mediators are present in the plasma in precursor forms that must be activated, usually by a series of proteolytic enzymes. The kinins increase capillary permeability and stimulate pain receptors. The clotting system traps exudates, microorganisms, and foreign bodies. The complement cascade causes vasodilation, promotes leukocyte chemotaxis, and augments phagocytosis. Acute inflammation comprises a variety of complex protective responses to injury that together lay the groundwork for the next stages of the body's recovery: immune response and tissue repair.
So that was a really explanatory video of everything that we went through. I mean, you can ignore bradykinin and serotonin. I mean, I don't mention that, but you saw all of this which we discussed, how it happens. And then look at that, it mentioned complement, and I wanted you all to see this video on complement. So let's go back to the first slide here.
The membrane attack complex is part of the complement system, which exists to aid in inflammation, phagocytosis, and other aspects of the immune defense, including pathogens from the body. There are two primary stages in which the complex is formed. The first is referred to as initiation. During initiation, protein C5b binds C6 and C7. The newly formed C5b67 complex binds to the membrane by C7. The second stage through which the complex destroys a pathogen is referred to as the polymerization stage. C8 binds to the complex and is able to insert itself into the membrane because of traits relating to the polarity of the molecules that make up the membrane and the protein itself. C8 is then able to induce many C9 proteins to form into a porous structure that penetrates the cell surface, filling it with water and oils, inevitably destroying the cell.
So it was a bit muffled, unfortunately, but what I wanted you to see there is that, remember I told you complement was in an inactive form and it tends to get activated, and there are many complement proteins, just as when we did clotting, there were many clotting factors. So when one gets activated, that activates another one, and then you saw how it kind of got stuck to the surface of the cell membrane and then caused lysis of the cell. So that basically was, however muffled it was, at least you could see that part of what was happening. And complement is important because it takes part both in non-specific immunity and specific immunity, which is also called adaptive immunity. Okay? So let's now go on to so we had gone through all of this. And this was where we were talking. We talked of the humoral response, the various classes of antibodies, what each one does. And here is one particular thing for now that I want you to pay attention to, apart from everything else. Humoral response produces antibodies. And notice here something called activated B cells. Okay, so once they come in contact with the antigen, the B cells which have the receptors for that specific antigen, they then get activated and then they form these clones. Okay, so just keep in mind this activation, because when we talk of another type of cell called helper T cell, we'll see how actually the helper T cell helps to activate B cells, and then the B cells can go on and do the rest of all of this clone formation. So here, once in humoral response, once an antigen combines with an antibody, you get an antigen-antibody complex that is formed, and the antigen-antibody complex is removed from the body. Antigen-antibody complex is not a cell. It is like proteins which are stuck to each other. They need to be removed from the body. And this is done in a variety of ways, and we call this plan. The P of the plan is it causes precipitation. That means the antibody binds to the antigen and precipitates it, so it becomes soluble and then it's removed from the kidney. So again, you can see it's removed from the body. This is one way which happens in blood transfusion. Remember how antigen antibodies combine in mismatched blood transfusion, and that's why if the blood transfusion is mismatched, the kidney is the organ which is affected the most because it has to be filtered out of the kidney. So P stands for precipitation. L stands for lysis, because antigen antibody complexes activate that complement system that we just saw. Remember, that was acting in non-specific. Now you can see how it's acting in specific immunity, also known as adaptive immunity. So when it activates complement then attaches to the surface of the cell and causes cell lysis. So the L stands for cell lysis. The complement also brings about phagocytes to that area, so phagocytosis is also encouraged, as well as inflammation. So you can see this complement causes lysis and enhances phagocytosis and inflammation. The A stands for agglutination. This is again something that happens in blood transfusion, where the red blood cells, whenever there's mismatch, they kind of stick to each other and they agglutinate. And again, they can go and on the kidney filtration membrane, they can go and block that kidney filtration membrane, which is why the kidney is most affected. And N stands for neutralization, where the antibody complexes, they neutralize the antigen. So neutralize, for example, bacterial toxins like rabies virus gives off a toxin, the rabies toxin. Tetanus bacteria gives off the tetanus toxin, so they help to neutralize it. So this is the way antigen antibody complexes, when they form, this is the way that they finally act. Okay, so it's not a cell that is formed, these are proteins which get together, and this protein complex either causes precipitation or causes cell lysis by activating complement, or causes agglutination, or causes neutralization of the antigen. So let's take a look at this question. Which of the following statements is correct? All are correct. Yes, very good. Think of this. The first one, of course, is correct, and everybody hopefully, no, some people didn't think of that one. Humoral immunity does involve cloning of B lymphocytes, because B lymphocytes take part in humoral immunity. Humoral immunity does involve the production of antibodies. Plasma cells do take part in humoral immunity, because when the B lymphocytes clone, most of them turn into plasma cells, and it's the plasma cells which actually form the antibodies. So plasma cells do take part. Humoral immunity is antigen specific, because it only reacts, each lymphocyte only reacts to the antigen for which it has receptors. So all of the statements are true. This one. Complement proteins support both specific and non-specific immunity. I think I mentioned this a million times. So everybody should get this correct. It is true. In non-specific, it was one of the second lines of defense, and in specific, we just saw in humoral immunity how humoral immunity activates the complement system. Okay, in humoral immunity, we have something called acquired immunity, and this is divided into two types. One is called active acquired immunity. So humoral immunity is the production of, is where antibodies are seen. It acts through the production of antibodies. In active immunity, the body is provoked, and your body produces the antibodies. Okay, so that's active. The body is actively doing some work. In passive immunity, ready-made antibodies are given to the person. So it goes, ready-made antibodies are injected into the body. So the body is not doing any work. It's sitting passively getting the antibodies. The first one, it's active. It's doing some work. So it's like this. I may have mentioned this before, but how many of you have bought your own cars? You just got a new one? Good for you. 1, 2, 3, 4, 5, 6, 7. My God, the rest of you are spoiled. Huh. What's it?
Last class we talked about that.
We did talk about it, yeah, right? So you got another car. Good for you. So you got 2 cars now?
No, he just bought another one.
Okay, good. So it's like this. So you guys are active immunity who bought your own car because you worked for it and you paid for it and you bought your own car. What's going to happen? It's going to live very long because you're going to take care of it, right? You're going to make sure that it goes through the car wash every week and oil change and all of that stuff goes on. So active immunity is long lasting. You're producing the antibodies. So when you do work, you like to make sure it lasts for a long time. Those of you who have parents who bought your cars, you're passive. Your parents gave you the car, right? So they gave you the antibodies. And because they gave it to you, not, okay, I got a car, it was given to me. I didn't have to really work very hard for it. You're probably not going to take that good care of it unless your parents really threatened you or something. But let's pretend that they didn't. So it's going to, you'll find it dirty within about 6 months, and then, the scratch and a dent here and there and so on. So your car won't last that long. Okay, I'm kind of, this is not true for everybody, but let me use this anomaly. So here, passive immunity is short lasting because the body didn't do any work. It was given ready-made antibodies. In both cases, see, I'm using the word antibodies. So because humoral immunity has to do with antibodies. So in active immunity, you produce the antibody. Your body produces the antibodies. In passive immunity, it is given the antibodies. Another name for antibodies, can anyone tell me? Immunoglobulin, very good. Immunoglobulin is a name for antibody. And gamma globulin, or IgG was immunoglobulin, gamma globulin, or we often also, you might say, immune serum, because remember, serum is nothing but plasma which has some proteins which have been removed. And where are antibodies present? In the plasma, right? So immune serum. So any of these three terms can be used for antibodies. So having understood the difference between active and passive, let's look at the ways we can actually get active and passive immunity. Active immunity could be where it is naturally acquired. In other words, when we say naturally acquired, that means it's something that happens in nature. So for example, let's say you get a viral infection. Let's say the measles virus gets inside you. It provokes your body begins to form antibodies. So for that first time, yes, you got the infection, but you produced antibodies, and they often tell you, don't they, that once you get an infection, you kind of have for some diseases, you have lifelong immunity, because when you get that, remember, it forms memory cells. And so if you were to get the infection again, the next time virus enters your body, those memory cells would react to it and, would prevent you from getting infected. But this is occurring naturally. The virus is all around you, so it gets into your body naturally, okay? So getting an actual infection or getting a pathogen inside you is called naturally acquired, and your body is provoked to forming antibodies. Artificially acquired is that when you get vaccinated. So we don't want to suffer from the disease, so that's why from childhood we get this series of immunizations where the antigen, let's say the measles antigen or the chickenpox antigen, the viral antigen, is actually injected into your body. So it's in a way to provoke your body into producing antibodies. But this is artificial because you've got to do something and you're artificially putting it into your body. But you might wonder, why would you want to give somebody the measles vaccine and cause them to have the disease? But you know that when you get a shot or vaccination, you don't actually get the disease. That is because the viral antigen is what is called attenuated. Attenuated means it is changed in such a fashion that it provokes the immune response, but it doesn't cause the disease. So it provokes your body to produce antibodies against measles, but you don't get the disease. Or sometimes many of these vaccines may have the antigen which is killed. So it's called a dead antigen, where it can still provoke the response, but you don't actually get the disease, okay? So either it can be changed slightly, so it's a live, what's called a live vaccine, or it could, the antigen itself could be killed by various methods, so that it provokes the response but doesn't cause the disease, okay? You had a question?
Yeah, what happens when you get one of those vaccines and you actually get it? Like, for instance, when I was a kid, I got vaccinated for chickenpox, and the next week I actually had it.
Sometimes a couple of things happen. So the question was like, what happens when you get the vaccination and then you actually get the disease sooner, soon after? One of the things could be maybe it was a bit strong there, or it could be that maybe the timing was such that you actually had the virus inside you when you were vaccinated, and so you would have had, whether you were vaccinated or not, you would have had the disease as such. And especially in childhood that happens, because this vaccine, the moment you inject the vaccine, it's not like you get immunity straight on, right? It's a primary response. It takes some time for the antibody to form. So that could be one of the reasons that happens, okay? Yes.
So if you have, you've had chickenpox, so now you've had the virus chickenpox, and now you build up a defense against it. How does that eventually morph into people getting shingles or something like that?
That is because shingles is caused by the chickenpox virus, but it is a different form of the disease. What happens is that the virus gets inside you, okay? You don't manifest with chickenpox because you have produced antibodies and so on, and the virus may be lying dormant inside you for a really, really long time. As you get older, your immune system kind of is broken down, or rather kind of regresses a little bit, and now that chickenpox virus finds that, okay, I can wake up and the immune system is not good enough to kind of control me, and then that manifests as shingles.
Is that why the shingles vaccine, you can't get it until you're...
Yes, there's no point getting it much earlier. You're never going to manifest with the disease, so that's why when you're older that they tell you to get that, to get the vaccine for that, okay? With this, you understand that now what happens is that in many cases, in many times, what happens when you get a vaccine, like I said, it's like mimicking the disease, but you don't actually have the disease. So vaccine has gone inside you, you produce antibodies, you'll produce that clone, you'll produce the memory cells, and should the pathogen get inside you, those memory cells take care of it, which is why you never get the disease. So you keep sort of get reinfected and memory cells keep forming and so on. This has a downside to it. Sometimes when we abolish certain diseases, like for example, smallpox is abolished, right? And then they started getting worried if there was germ warfare and smallpox virus was thrown in. We've all lost immunity. We may have had I don't know if some of you may not even have had the smallpox vaccine because it may have been eradicated by the time you guys were born or whatever. But even if you had it, what happened is since the virus has been eradicated, it never gets inside you. So those memory cells die after some time. So you never form those, a continuity of the memory cells. So now, if, for example, the virus gets reintroduced into the atmosphere and it gets inside you, there are no memory cells. So it becomes like you've never got the vaccine. And so you can react to it, which is why, soldiers and so on, when they suspected that they could be germ warfare, they were advised to get the smallpox vaccines. And this is what happens when you eradicate a disease. Since memory cells, they form, but then since you don't get reintroduced to the virus or the bacteria, you don't keep forming a continuity of memory cells. Memory cells are not lifelong. They keep having to be produced. They last for a very long time. But since you get reintroduced, they form again. So you can see it's like, so, they keep kind of being continued to form. If the virus is no longer there, once those memory cells are formed and outlive them, you don't form anymore. So it's like back to square one. So if this virus comes back into circulation, then it is as if you never saw it again and you end up with the disease, okay? Unless you get vaccinated. You had a question?
How long does it normally take for the virus, once you get introduced to it, how long does it take for it to not remember anymore?
I can't give you, in other words, you're asking me what is the lifetime of a memory cell. I don't know. It is different for probably every different kind of an antigen. They last pretty long. But I can't give you in time in years, like it's 5 years or 10 years. And maybe it's also because we know that we are going to keep getting reintroduced because measles virus is there in the atmosphere. So if you've had a measles vaccination, you're good because the virus is floating around, so it gets into your body. The memory cells will recognize it. They'll mount a secondary response where more memory cells will be formed. So you see, if one is 2 years old, now you get a fresh one, and that's going to form and last so long. So since you keep getting reintroduced, keep getting fresh batches of memory cells being produced throughout life. You see that? So I really don't know the answer to how long they last. They last very long. But if after some time there's no introduction of that virus, these have died, and so then you're back to square one.
I work in the emergency room, and like is it true that your immune system gets a lot more stronger because you're working
Yes.
around all the sick people?
Yes.
Okay,
Yeah.
that's what I thought.
Yeah. The more you keep getting introduced to these, you kind of build up the immunity. So yes, it's good. But it also has a downside. You might, if you for some reason were sick, then you may be more prone
Yeah,
to.
I get the sniffles sometimes. I'm like, oh.
Yeah, because cold virus is, like I said, many strains and okay.
Okay.
So that is active natural and active artificial. Let's look at passive. Passive is where you introduced antibodies. You gave ready-made antibodies to the person. This also could be naturally acquired, and one good example is, like, for example, a fetus getting antibodies from the mother through the umbilical cord and through the placenta or through breast milk, which is why we like to make sure, like, the mother is well immunized before she gets pregnant, so that she has all the antibodies that she needs to have so that she can transfer it to the fetus. And secondly, we also say as soon as the baby is born, we like the mother to begin nursing immediately, and the first breast milk that comes out is known as colostrum. It's a little thick, and this contains a whole heap of antibodies. So the more the mother lactates, especially during the first 6 months, there are enough antibodies which are passed from the mother to the fetus, to the baby now, and so the baby till 6 months is well protected. So you really do not need to start immunizing before 6 months. The baby is well protected. But sometimes, we start certain vaccinations very early, and we kind of build up a regimen so that, we kind of spread it out and go on till school going age. So this is naturally acquired. Yeah. Go ahead.
I've heard about naturally acquired immunity several times, and I've really only heard of this example with breast milk. Can you think of any other naturally acquired examples? Or is that kind of it?
Through breast milk and through the placenta. Yeah. None that I can think of. Yeah.
So what happens, like, if the mother has problems nursing and doesn't end up breastfeeding the child?
Well, if the mother is not able to breastfeed the child, obviously the child will not get the antibody. So we'll start out with a weak immune system, and you just have to be more careful.
Right.
Yeah, you just have to be careful. As long as the child is, well looked after and so on, hopefully the child will not suffer much. But then, the child doesn't get those first 6 months of protection. The child is not getting that. Little bit it does get, because through the placenta the child has got that, but through breast milk, no. Okay. Artificially acquired passive immunity is when you're artificially giving immunoglobulins or antibodies or gamma globulins or immune serum, and this is done when you quickly want to establish immunity. So imagine someone is bitten by a rabid dog. You cannot wait to give a vaccine which will start developing antibodies, because remember, that takes some time. By the time the person will die of rabies, right? So you immediately want to give them antibodies so that then those antibodies can react with the rabies virus and take care of it right then. So that's an example of giving ready-made antibodies. Since again you're injecting it, so this is artificial, but it is passive artificial immunity. Okay. Tetanus, if someone got, let's say, a rusted nail or something like that, or you kind of suspect that this person is going to get tetanus, again, there's no point giving the tetanus vaccine to them. You want to give them the immune serum so that the immunity is established right away, and that can take care of the disease. Okay?
So which is the difference between active artificial and passive artificial?
active artificial and passive artificial. In active artificial, you're giving a vaccine where the body will produce antibodies, so this takes time. Okay? In passive artificial, you're not giving a vaccine, you're giving immune serum. That means you're here in the vaccine, antigens are present. In passive artificial, you're giving them immune serum which has antibodies with it. So you're giving the person antibodies, ready-made antibodies. Okay? Here you're giving them antigen, hoping that now the immune system will be provoked and they will form antibodies. Followed? So I have a few questions which you should be able to answer. So let's take a look at this. When you give ROGAM, so when we did blood, we did this, right? We gave anti-D antibodies. Remember, just before delivery and soon after delivery, within 72 hours, if an Rh negative mother had an Rh positive fetus, we gave her ROGAM. What are you giving her? Very good. You're giving her passive artificial. Here's how you should have been thinking about this if you got it wrong. You are giving, see, I use the word antibodies. So when you're giving her antibodies, she's passively sitting there and getting the car. Think of it like that. So it cannot be active. Because active immunity is when you have to do work. You have to buy the car. That means you have to make the antibodies. Okay, so it shouldn't have been this answer. In this natural, remember Sarah just said natural was two ways, that either lactation or through breast milk, meaning it's occurring naturally through the body. So it's not passive. It's not passive natural. It is passive, but it's not natural. This is you're receiving antibodies, so it is passive, but it is artificially introduced because you inject it into her. So it is artificially introduced. So this is passive artificial. Okay? Let's look at a few more examples. When you take a flu shot in winter, what are you doing? And that's why always look at the words which are associated with what I'm asking. Good, active artificial, excellent, yes. Okay, so let's look at cell mediated. So now we had done humoral immunity, now we're going to do cell mediated immunity. And again, look, it's a type of specific, and again, specific is also known as adaptive immunity. So in this, T lymphocytes, the ones which were in the which got immunocompetent in the thymus, these are the ones which take part. The T lymphocytes are divided into a few cell types. There's this one called cytotoxic. This is the one which is toxic to cyto or cells. This is the one which actually kills the cells off. So it's a cell-to-cell interaction. So cells will interact with cells. For example, if you have a graft, if you give somebody a graft, let's say somebody got burnt real terribly, and instead of taking skin from their own person, you took the skin from somebody else, and that graft was rejected. There was a cell-to-cell interaction, it was thrown off. Or you do transplantations. You've seen so many times transplantation rejections which occur, because again, there are cells which are thrown off. And when viruses get inside the cell, remember I told you viruses enter the cell and they replicate, and that's their means of causing propagation of the disease, and interferon is what prevents that viral replication. So viral infected cells and destruction of these, all these are examples of cell-to-cell reaction. And this is done by cytotoxic T cells, which are also called CD8 cells. Then we have helper T cells, which are called CD4 cells, and these are very important, and we'll see them. Then we have these regulatory T cells, also sometimes called suppressor T cells, which kind of will make sure that the immune system is turned off once whatever you want to be done is done. And then Just like we had memory cells formed in the humoral immunity, you have memory T cells formed in this as well. So let's look at what happens up here, and here we are kind of paying attention to the helper T cells and why the helper T cells are very important. For now you can kind of, I don't particularly want you to remember where class 2 and class 1 Mhc proteins are used, but I do want you to kind of, we all did Mhc proteins, remember the major histocompatibility proteins which wave the marker, the antigen. So let's take a look at this. So in this kind of response, the antigen has to be engulfed by an antigen presenting cell. Then it has to attach to an Mhc protein. That Mhc protein has to kind of process it and wave it on its outside. And then only these T lymphocytes can recognize the antigen. So they cannot recognize the antigen floating free in the extracellular fluid like B lymphocytes could. Okay. So let's see what happens. So here is a antigen presenting cell. Remember the types were B lymphocytes, then we had natural killer cells, and here is a dendritic cell. So an antigen is there, it goes inside. This dendritic cell is a phagocytic cell. It kind of phagocytoses it, processes it, and attaches it to a different type of Mhc protein, but we can forget the class 2. So the Mhc protein processes it and holds it up. And it also, this dendritic cell also has a little kind of a stick which you can see here, which is called a co-stimulatory molecule. This dendritic cell is now floating around, and a helper T cell, a CD4 cell, which is lying over there, that comes by and that recognizes this antigen up here. It recognizes the Mhc protein as well, and it also has its own CD4 protein up here. So because it recognizes the antigen and the Mhc protein, they kind of fit together well. The CD4 protein and there's a co-stimulatory molecule from this side, which the two kind of attach to each other. This is just extraneous information just to kind of show you that everything fits in like a real nice jigsaw puzzle. The idea of this co-stimulatory molecules fitting to each other is they stimulate this clone formation, okay? So you can see once this recognition appears, clone formation occurs. So many more helper T cells are formed, and a memory T cell is formed at the same time. This helper T cell will actually then go and activate cytotoxic T cells, and it will also go and activate those B lymphocytes so that humoral immunity can take place and cell-mediated immunity can take place. Remember when I went back to that humoral immunity, I circled that activated B cell. I told you I'll pay attention to that. That activation of the B cell is stimulated by this helper T cell, and we'll come back to it, but here I just want you to kind of remember this, okay? So have you understood this? So here's an antigen presenting cell presenting the antigen. After processing it, a CD4 cell, a helper T cell comes by, recognizes it. It forms clones, forms many more helper T cells, and some remain as memory cells. This then goes on to activate cytotoxic T cells, and later we'll see it also will activate B cells. Now let's take over how cytotoxic T cells act. So here in cell-mediated immunity, as I said, it's a cell-to-cell reaction. So the cytotoxic T cell, it recognizes an antigen presented by the target cell. So Mhc proteins on the target cell, it recognizes that. It quickly goes and attaches to it. When it attaches to it, it liberates substances called perforins. It liberates substances called granzyme, and also liberates substances called lymphotoxins. As the name suggests, perforins actually perforate the cell membrane. The granzymes get through pores in the cell and they go inside where they trigger enzymes, and those enzymes cause the cells to lyse. These perforins target the cell membrane, so the cell membrane kind of has little holes, so again the cell lysis occurs. So the end result is that the cell is lysed, And then this T lymphocyte goes out, this cytotoxic T lymphocyte goes in search of another prey. So you can see as it's traveling, it's killing off cells. And here you can see it's a cell attaching to a cell. So can you see that's why it's a cell-to-cell interaction, okay? So here now we are coming back to that importance of that helper T cells. So see how helper T cells are perhaps the most important cells in the immune system, because as the name suggests, they help. They actually help the B lymphocytes carry out their function. They help the T lymphocytes carry out their function. If they were not present, the B and the T lymphocytes would not be able to do their job properly. So here's what happens. So how they help in humoral immunity. So here's a helper T cell, and with its Mhc protein, and it's got the antigen up here. It attaches to a B cell which has processed that antigen and is displaying it on its surface. So they interact, and this helper T cell now because it secretes interleukin. IL stands for interleukin, and it secretes other molecules. It secretes something known as interleukin, and it secretes cytokines. These are molecules which help to activate the B lymphocyte. So now when the B lymphocyte gets activated, this then starts forming clones. Of those clones, most of them form those plasma cells, a few remain as memory cells. Do you see that? So what we had done earlier when we talked of humoral immunity is we had taken it from this point. But in order for this B lymphocyte to get activated, it actually has to be helped by the helper T cell. And that helper T cell liberates these cytokines, cytokines and interleukins once it attaches to a B lymphocyte with the same antigen. Okay? So that's how humoral immunity is helped. Let's see what happens in cellular immunity. So here is a dendritic cell and the helper T cell attached to it, like we saw in the previous picture. This dendritic cell again has this antigen, and a T lymphocyte is also attached to it. But this T lymphocyte becomes activated because this helper T cell again liberates those co-stimulatory molecules which are interleukins and so on. And therefore this CD8 cell becomes fully activated, and then it will form clones and it will be able to do its job. If this was not there, these molecules would not be liberated, this would not get activated, and hence it would not be able to do its job. So can you see how it's helping both in humoral immunity and in cell-mediated immunity, and that's why it's called helper T cell. In AIDS, what does AIDS stand for?
Lack of immunity.
Pardon? Okay, someone said autoimmune deficiency syndrome. So autoimmune deficiency syndrome. Does everybody agree?
Acquired.
Yes, it's not autoimmune. There's a difference. It's acquired. Because you acquire it. Acquired immune deficiency syndrome. You have acquired this state of immune deficiency. Okay? You have acquired this state of immune deficiency. That means your immune system is deficient. It's not able to do its job. Why? And this is done by a virus, the human immune deficiency virus. What the human deficiency virus does is it targets these helper T cells. So these it kills off the helper T cells, which are the CD4 cells. So when somebody gets the HIV infection at first, they don't manifest with AIDS right away. It kills off CD4 cells. So let's say that there were billions of CD4 cells. It kills a certain percentage. You still have a lot left, so your immune system is still functioning. When it keeps killing these helper T cells, your helper T cell numbers come down. When your helper T cells numbers come down beyond a certain level, then you begin to manifest with AIDS, where your immune system becomes deficient and you fall prey to all sorts of infections which you normally would not have fallen prey to, like fungal infections Most of them are fungal infections or really common colds, all those things which you previously could fight against, now you're not able to fight against because your immune system is slowly becoming more and more deficient. And that's because helper T cells numbers are falling down. If their numbers go so down that they're not able to help the humoral and cell-mediated immunity do their action, immune system becomes deficient. Yeah.
So some of the medications that people with HIV take, does it give them helper T cells?
No, it doesn't give them the helper T cells. It helps to prevent the viral replication, so it prevents the spreading.
Is there any medication that can give these people?
Well, you can give, you can't give a medication that gives them helper T cells, but you can give them immunotherapy where you can give them, you can transfuse lymphocytes into them, like that, the helper T cells. You can do that, but you can't give them a drug which will give them helper T cells, okay? So let's look at the humoral and cell-mediated immunity. So let's review these.
The body's humoral, or antibody-mediated immune response, begins in the same manner as its cell-mediated response. But here, the macrophages are joined by lymphocytes, called B cells. The pathogen activates only those B cells with matching receptors. These cells stand ready to enter the battle. Meanwhile, the antigen-presenting macrophages activate those helper T cells with matching receptors. These, in turn, rendezvous with activated B cells. Triggered by this meeting, the helpers release chemicals which spur the selected B cells into rapid reproduction. Some B cells become memory cells, ready to respond to a later invasion by the same pathogen. But most become antibody-producing factories, called plasma cells. Freely circulating in the body, antibodies dock with pathogens. This neutralizes them, or marks them for destruction by other weapons in our immune arsenal.
So that explained humoral immunity. Let's take a look at cell-mediated immunity.
White blood cells, called macrophages, lead the body's cell-mediated immune response by engulfing and digesting foreign invaders. Combining peptide fragments from the invaders with some of its own proteins, the macrophage builds a patchwork of antigen complexes on its surface. When smaller white blood cells called helper T cells encounter the macrophage, those with matching receptors bind to its surface. These helpers then multiply and secrete chemicals which call different cells into battle, especially the cytotoxic or killer T cells. The macrophage, or an infected cell, activates only those cytotoxic cells with receptors that match the antigen complexes. Stimulated by chemicals from the helper T cells, these killer T cells rapidly divide into an army of clones, all designed to fight the specific invader that triggered the response. When killer cells dock with an infected cell, they bombard it with lethal toxins, then move on in search of other targets.
So here is a really good slide. I know this slide looks extremely busy, but if you kind of pay attention to it, this really explains the entire immune system. One is, as I said earlier, it isn't as if when a pathogen enters your body that the body decides, I'm going to use only innate or non-specific immunity, or I'm going to use adaptive or specific immunity. Everything kind of occurs side by side. And the idea is that if one system is able to control it, it'll stop there. If it's not able to control it, it'll go through everything. So let's take a look up here as, let's say, an antigen gets into the body. So it's triggering off the innate is non-specific response. So first the surface barriers try to control it. Let's say it doesn't manage to control it. Then it triggers the second line of defense. Let's say that also is not able to control it. This will now trigger off the adaptive response. Sometimes it may be that it triggers off everything together so that the entire, it's kind of the pathogen is overwhelmed by all of this. So here in the adaptive response, it's triggering off humoral on this side and cell mediated on this side, okay? So I'm going to kind of go this way. So let's say here a dendritic cell attaches to that antigen and it processes the antigen and on its surface with the Mhc protein. Then this activates helper T cells. Helper T cells will clone. Some will form memory T cells and some will form helper T cells. These helper T cells, you can see, they interact with B lymphocytes. These are B lymphocytes which have come in contact with that antigen. Those B lymphocytes interact with the helper T cell. The helper T cell sort of stimulates them to form clones. So it forms many plasma cells and some remain as memory cells. The plasma cells form antibodies. The antibodies go and react with that antigen and they neutralize it or cause precipitation and all of that, like we saw. On this other side, the same helper T cell which was stimulated and activated, this liberates cytokines and it induces this CD8 or cytotoxic T cells. It kind of stimulates that. Those form many clones of cytotoxic T cells, some memory cells remain, and these then go and have a cell-to-cell interaction with that, where that antigen is present, and they take care of that. So can you see that all of this occurs all together, okay? Sometimes it might be you have a mild infection, your surface barrier is enough, and that's where it stops. Sometimes the infection may be so intense that it goes all the way, everything is stimulated together, okay? Okay, so let's answer a few questions up here. Cell-mediated immunity would not be seen in which one of these? Okay, the correct answer is mismatched blood transfusion. Remember in blood transfusion we had antigen antibody reaction that was occurring. Graft rejection, it was cell. Remember I said it was cells taken from somewhere and put on, say, your body, and the graft is rejected. Body, I didn't mention this when we were talking, but cancer cells, see, cancer cells are being destroyed. So it was a cell-to-cell interaction. So your body tries to destroy cancer cells. Same with virus infected cells. The virus has gone inside the cell and cytotoxic T cells come and attach to that and they kill it off. So these three are all examples of cell mediated immunity. There's a cell to cell interaction. Here in mismatched blood transfusion, we did that when we did blood. It was antibodies were being formed, which is part of humoral immunity. Those antibodies attach to the antigen and form an antigen antibody complex. Another question, what will happen if the helper T cells are destroyed? Immune system will not be affected. Yes, the cell-mediated immunity will suffer, but in a multiple choice question, you always have to choose the best answer. The immune system will not be affected because it's not only the cell-mediated, it's also humoral immunity which will suffer, which means that the immune system will not be affected, okay? Here, another question. What is the difference between autoimmunity and AIDS? The spelling here is wrong. Very good. Yes. In autoimmunity, it's autoimmunity against self. So the immune system cells are not able to recognize self. So that recognition apparatus has broken down due to some reason. Okay, so that's why it's autoimmunity. Examples of did we go over the diseases that we see in autoimmunity? Did I go over some of them? Multiple sclerosis. Can you tell me some more examples? Rheumatoid arthritis. Psoriasis is one. I think I went over this. I didn't. Okay. Psoriasis. Type 1 diabetes. There's a disease we'll do which is called Graves' disease, which is a disease of the thyroid gland. And all of these antibodies of a myasthenia gravis is another disease. So many. All of these are when antibodies are produced and they attack the body cell. So like in multiple sclerosis, the myelin is affected. So it's attacked. So there's demyelination. In Graves' disease, we have antibodies which resemble something called TSH. So that is affected. So in all of this, the body is attacking itself. In AIDS, the immune system is poorly functioning because the CD4 or helper T cells have been destroyed. So the immune system is poorly functioning. This is 2. It's not that the immune system has not developed in autoimmunity. It has developed, but on the other hand, it's kind of acting weirdly. It's acting against itself, okay? Let's look at this, which is allergy and hypersensitive reaction. You may have all experienced this living in Florida, especially now when the pollen count is really high. We all have the sniffles. So let's see what happens. There are 2 stages which happen in this hypersensitivity reaction or allergy, and this is a case where the immune system goes into panic mode. Or it hyperreacts. That's why it's called hypersensitive reaction. So the first thing that happens is that whatever antigen is present, which is called an allergen, it could be pollen, you could be allergic to eggs, you could be allergic to shellfish, everybody is allergic, different, some people are allergic to food coloring, different things. That allergen enters the body, and what it does is it goes to the plasma cells and it causes the plasma cells to produce antibodies against that allergen. Those antibodies which are produced are IgE antibodies. So that's why, again, very important to look at slides very, very carefully. You'll see the answers in the slides itself. IgE antibodies. Those IgE antibodies go and attach to mast cells and basophils. Mast cells and basophils contain granules which have histamine and heparin. So this is the first time it happens, and this is called the sensitization stage. You don't know when it happened. When you do get the sniffles, what happens is this is the subsequent exposures to the allergen. So these are called secondary responses. So more of the same antigen comes into the body. Now it quickly goes and attaches to the antibodies which are present on those mast cells or basophils. When they attach, this antigen-antibody complex causes the granules inside the basophils and the mast cells to degranulate. So they release histamine and heparin. This histamine and heparin go into the system and they cause the capillaries to vasodilate. When they vasodilate, fluid seeps out and that causes edema. You may have noticed people who have any allergic response, you can immediately see swelling of their face, their eyes may be swollen, they might find it difficult to breathe, they produce a lot of mucus. All this is because of the release of histamine and heparin. So the histamine causes vasodilation of the capillaries, it causes release of mucus from the glands, which is why people sort of start tearing up sometimes because, the tear glands get stimulated. The bronchi constrict, so somebody may have a very, very severe reaction which is known as, a very severe hypersensitive reaction is known as an anaphylactic reaction. or anaphylaxis, where the person can't breathe, they choke, and that's because the bronchi constrict. When the bronchi constrict, air cannot go in, so you cannot breathe properly. The vocal cords, just above the vocal cords, there is a swelling which is known as vestibular folds. Those close up, so the airway is blocked there itself. And severe swelling these people have, and that's because of the histamine and heparin which is released. So let's take a look at this.
Normally, your immune system helps protect you. It does this by sending in special cells, proteins, and natural chemicals whenever viruses, bacteria, or other harmful substances invade your body. This response helps neutralize the foreign invaders. But there are many things that enter your body that the immune system views as harmless. This can include things like pet hair, dust mites, and tree, weed, or grass pollen. In a person with allergies, the immune system mistakes these harmless substances, known as allergens, for a potential threat. The first time the immune system sees an allergen, it reacts by activating special cells. These cells make large amounts of proteins, called antibodies, that are specific to the type of allergen. These antibodies then attach to other immune cells, making them sensitive to the specific allergen. The next time the allergen enters the body, these sensitive immune cells quickly attack. They attach to the allergen, which causes a release of natural chemicals, including histamine. These chemicals enter the surrounding tissue and cause many of the early symptoms of allergies. For a person with allergic rhinitis, which affects the nose and eyes, sneezing, an itchy, runny nose, and red, itchy, watery eyes can result. 2 to 4 hours later, another response begins as more immune cells become activated and release their chemicals. These chemicals cause inflammation, swelling, and congestion within the affected areas.
So you can see this is why, since histamine is one of the mediators which is released, whenever you have an allergy, you take antihistaminics, so you prevent the release of that histamine. And hay fever, like I said, is this allergic rhinitis that we get. It's called hay fever because it first was seen in the barns of England where hay was present. So let's take a quick look at some things that we've discussed throughout the system. What is the mode of action of interferon? NKC stands for natural killer cells. It is A and B. It does prevent replication of viruses, and it activates natural killer cells and macrophages. So that's the function of interferon. Okay, so if the thymus did not develop, what type of immunity would be compromised? Cell-mediated. Remember, thymus T lymphocytes become immunocompetent in the thymus, and T lymphocytes, that's why we call them thymus dependent. That's why they take part in, cell-mediated immunity. Humoral immunity is B lymphocytes, which go to the bone marrow. Complement proteins. Which of these applies to complement proteins? Very good. All of the above. Okay. Which class of immunoglobulin is liberated in allergic responses? I'd be very disappointed if we didn't get 100 on this one too. IgE, yes, IgE. IgG is most plentiful, but IgE is specific to allergic responses.